So if it says that it is increasing over the interval negative infinity to positive infinity, what does that mean?
Basically going from this side of the graph, or like from the bottom of the graph to the right side of the graph, like left to right, it's going up.
Okay, so it's going up. So what kind of exponential functions go up?
Positive.
What kind of, think back to yesterday.
1 through n.
What kind of exponential functions go up? What?
Growth.
Growth. Exponential growth functions go up. Okay, so this one is a growth. Because it's a growth, what else do we know?
It has to be, like the base number has to be over 1.
The b has to be greater than 1. Okay? Oops, I put 0. Tap the brakes. b has to be greater than 1. Okay? So give me an example of an exponential growth function where b is bigger than 1 that goes through the point 1, 6. Go.
6 to the x power.
F of x equals 6 to the x power. Does that go through 1, 6? Yes, it does. Okay? Give me another example of one. What about f of x equals 2 times 3 to the x power? Give me another one.
6 or 1 times 6 to the x power.
That's the same as one that you gave me before. Give me another one.
3 times 2 to the x power.
1/2 times 12 to the x power.
There you go. Now we're thinking. All of those functions have a reference point or a common point of 1, 6. If you plug 1 in for x into all 4 of those functions, you get an output of 6. Okay. Part B, decreasing over the interval negative infinity to positive infinity. What does that mean to us in finding the function?
Flip the other way. So it's not a growth, but decay.
It's a what?
Decay. Yeah.
Decay? Okay, so this one is a decay. So what does that mean?
It's going left to right down the
B has to be greater than 0, but less than 1. Okay. And it's got to go through the point -1, 4. Okay. Give me an example of an exponential decay function that goes through -1, 4.
0.4 to the x power.
0.4 to the x power does not.
I think.
No.
Wait, would it be 1/4?
1/4 to the x power would. Give me another one. that's a growth function. Nope.
Would it be 2 times half to the x power?
Oh, is it the, can I do the other way around? Can I go 8 times 1/2 to the x power?
No, but you can go 2 times 1/2 to the x power. 8 times 1/2 to the x power would go through the point -1 comma 16.
Oh, these ones kind of confuse me.
Give me another one. You got it, Kevin.
1/2 times 1/8 to the x power.
Just because I like symmetry, give me one more.
Times 1/16.
All of those go through the point -1 comma 4. Okay. At the bottom of page 755, I would like to spend a little bit of time talking about the characteristics of exponential growth and exponential decay functions. So our function is going to be f of x equals a times b to the x power. Okay. So if we are in a growth case, b is greater than 1. If we are in a decay case, b is between 0 and 1. Okay? So the domain for both of those, domain, remember, is x values that you can put into the function. Okay? What is the domain for both of those cases, both growth and decay?
They're both exponents.
What can I put into the function? That's what domain is. Domain is what you put into the function.
Would it be 0 comma infinity for the exponential growth?
Okay? So what you're saying by saying that it's the domain is from 0 to positive infinity is you're saying that we can't put in any negative numbers.
Oh, yeah. We're just
So what's another word that we call that? All real numbers. Yep. In both of these, there is no x value that you can't put in. Okay. Remember, okay, so that's because our functions here look like an exponential, we'll put it in red, an exponential growth function looks like that. An exponential decay function looks like that. Now the range then is the values that you get out of the function. Okay? What would the range be for both of those functions?
All real numbers.
No. It can't be negative, right? Okay. What else can't it be? Nope, it can be 1.
0.
Can't be 0. Okay? So the range then would be y is greater than 0. In both cases. Remember that an asymptote is a line that our function approaches at either positive infinity or negative infinity, at the extremes. Is our functions approaching a certain value at one of the extremes? What's it approaching?
Either positive infinity or negative infinity.
Okay, but that's not a line. I can't make the line x equals infinity or y equals infinity.
Oh.
So go to the other side of each of the graphs.
All real numbers except.
Nope, it's a line. So it's either got to be y equals something or x equals something. What is my function approaching at on either side of the graph? So, like for instance, on this side of the graph right here, what's my function approaching? Infinity. Do I know infinity? No. So I'm not worried about that side up here. On this side, what's my function approaching? 0. Is it ever going to cross over 0? No. So wouldn't that be an asymptote? Well, what's the equation of my asymptote then?
X equals 0.
X equals 0 is a vertical line. Y equals 0. Now let's look at the decrease function. What's the asymptote there? Y equals 0. They're very similar. Intercepts. Okay? Will either of those functions cross the x-axis? No. So there's no x-intercepts at all. Do either of those functions cross the y-axis?
Yes.
Okay. So what are the coordinates of the intercepts? The y-intercepts. Let me be a little more specific. Okay. We bring back our function into play. How do I find the coordinates of the y-intercept?
Side equals 0.
No, that's for x-intercepts.
I'll plug 0 in for x.
Plug 0 in for x. So the y-intercepts are going to be of the form 0, comma something. What are the y-intercepts?
Where it crosses the y-axis.
What are the y-intercepts?
Oh,
We actually mentioned it yesterday.
positive numbers.
1.
Nope. Think back to my function. So what is the y-intercept? 0, comma a. If I put 0 back into my black function up there, I get out a. So my y-intercept in both cases is 0, comma a.
So you don't have to set it equal to 0, or you don't have to plug in 0.
I did plug in 0 for x, like you told me to.
But you can just find, but it'll
b
always
to the
be
0 power is?
one.
b to the 0 power is?
1.
1.
Yeah. So you can just take your a value, and that's going to be your y-intercept.
That's your y-intercept.
Okay.
Yep. Every time. Yep. End behavior now. And we'll go and do it. So, as x approaches positive infinity, what does my function do? And as x approaches negative infinity, what does my function do? in a growth case, as x is going to positive infinity, where's my function going? Positive or negative? It's going, my function is going to positive infinity. As x approaches negative infinity, what's my function doing? It is not approaching negative infinity. From above or below? Above. As x approaches positive infinity, what is my function doing? It's approaching 0 from above in a decay. As x approaches negative infinity, what is my function doing? Positive infinity. Function can never be negative. Intervals of increasing or decreasing. An exponential growth function is what?
Increasing.
Always? Only over a certain interval? Never? Always increasing? Okay. So this one is increasing. From negative infinity to positive infinity. Exponential decay function.
Negative infinity to 0.
It's always decreasing, right? No. If it's always decreasing, that means it's decreasing from negative infinity to positive infinity. It's right there in the title, decay. Okay? Increasing or decreasing, you work left to right. If the function's going up, it's increasing. If the function's going down, it's decreasing. Okay?
Just explain why. I don't really understand why they're the same.
They're not what? They're not the same.
With like the infinity stuff. Like,
Because on the left one, it's always increasing.
yeah.
So it will always grow. As you work left to right, it's always getting bigger. Okay? On the other one, it's always getting smaller, but as you work left to right. Yeah. They don't change, meaning they don't go like this. They don't go increasing, decreasing, increasing.
Okay.
You know what I mean?
Yeah.
They're always increasing or they're always decreasing.
Okay. So that's why the intervals are the same.
Yes. Okay? What I would like you and a shoulder partner to do now is I would like you to complete page 756. Numbers 1 through 4 and 6. Skipping number 5. Okay? 1 through 4 and 6. Okay? Alright, so let's compound some dough. Helen is opening her first savings account and is depositing $500 in it. Suppose she decides on a bank that offers 6% annual interest to be calculated at the end of each year. So you keep your money in their bank and then they give you the interest on December 31st of each year. Okay? So, recall that the formula for compound interest is A equals P times the quantity 1 plus R to the T power. Okay? Write a function A of T. So my function is going to be A of T. To model the amount of money in Helen's savings account after T years. So she started with $500 and her interest rate was 0.06 to the t power. So my a of t, then making it look nice and pretty, would be 500 times 1.06 to the t power.
Why isn't it 1.1306?
Because her interest rate was not 106%. Alright? You added the 1 twice, but you only have to do it once. Okay? Alright? Number 2, calculate the amount of money in Helen's savings account at the end of year 1. So that means that we would like to find A of 1, which would be 500 times 1.06 to the first power. 1.06 to the first power is 1.06. Okay, so this is 500 times 1.06, which is 500, I believe it's $30. Yep.
Wait, are they adding it or taking it out for interest?
So she earned $30 in interest.
I thought the bank would take it out.
No, interest is money that the bank gives you for them using your money.
Oh, I thought
Yeah.
it worked the other way around.
Nope. Okay. Number 3, how much money is in Helen's savings account at the end of 5 years? So now we're looking for A of 5, which is 500 times 1.06 to the 5th power, which I get to be rounded to the nearest penny, $669.11. Okay. Question number 4 says, suppose that the bank decides to start compounding interest at the end of every 6 months. So at the end of June, they compound the interest, and at the end of December, they again compound the interest. If they still want to offer 6% per year, how much interest would they then offer over the 6-month period?
3%.
3%? Because there are 2 6-month periods in the year. Okay. So that means that they are then going to compound twice. So 6% divided by 2 is going to be 3%. Which now then this 3% would become my new R in that formula. Okay? Not only does that new R come into play, but my T oops, that's a bad S. Looks like an 8. My T is also doubled because I'm compounding it twice per year, and t was number of years in that formula. So not only does my r get cut in half, but then my t would have to be doubled. Okay? Now, let me ask you a follow-up question to this one. What if the bank decided to compound it monthly? Okay? Still offering 6%. What would happen with my formula? So my formula again was A equals P times 1 plus R to the T.
So it'd be 0.002.
How did you come up with that?
12 months in a year.
Okay.
And you're at 6%.
So how did you come up with 0.002?
Well, 6 months, or 6%, divided by 12.
So R first, you would do what? 6%
Yep.
divided by
12 months.
12. Okay, what is 6% divided by 12?
0.0025.
It is not 0.0025.
Or 0.005.
0.005. Okay. Okay. So that's one thing that happens. What's the other thing that happens?
You gotta triple your T.
No.
TS 10 plus 6.
No.
Does it get multiplied 12 times?
By 12. Yep. Okay. So I divide my rate by 12, which then means I multiply my t by 12. Okay? Number 6, write a function to model the amount of money in Helen's savings account at the end of t years, compounded n times per year. Okay? So, what's going to happen to my interest rate? Following the pattern that we just set up down here. What's going to happen to my interest rate? How many times a year am I compounding it? How many times a year am I compounding it? N times. So what's going to happen to my interest rate? Which was 6%. I'm going to divide it by n. So my interest rate then is going to be 0.06 divided by n. Okay? What's going to happen to my exponent, the t value?
Oh, you're going to divide that by, multiply that by 10, or by n.
So my exponent then is going to be n times t, where t is still years, right? So my original formula was A equals P times 1 plus R to the t power. What happened to R? It's divided by n. So this becomes A. Oops, let me move over a little bit. This becomes A equals P times 1, times 1 plus r divided by n. And what exponent am I going to? The nt power, or t times n. Okay? Now, what you just developed there is called the compound interest formula. Okay? In maroon up here, that's simple interest, where you're only compounding it once. Okay? The compound interest formula allows you to compound things multiple times. So, P still is your starting amount. R is still your rate of change. T is still time, but that time is in years. And N is the number of times compounded per year. Okay? I think that's a good breaking point for today.